Hi CRUE, this is Parfait again with another training tutorial video. And today I'm going to quickly show how to model a low frequency sinusoid plate. I'm going to show it for lateral torsional buckling behavior and not for shear buckling behavior. But the basis of the low frequency sinusoid geometry can be found in this paper published by one of my former colleagues, Peter Wenck. And this paper goes in details about the LFS. So this is the paper here, low frequency sinusoid for enhanced shear buckling performance of thin plates, but I'm going to show it on how to do it with lateral torsional buckling for a simply supported beam under pure moment load and not under pure shear. So here is a typical LFS, and then here is the details of the geometry. The most important thing to remember is the relationship between the frequency and the wavelength and the amplitude and the depth. So a frequency basically means the number of half wavelength across a depth. And as you can see here, as Peter has explained, meaning that when you have a frequency of 2 along the longitudinal length of the plate, you will have 2 half wavelengths. When you have a frequency of 3 along the longitudinal plate, you will have 3 wavelengths for a distance of d, which is the depth of the web. So that is all. Now let's go to the modeling. So for the modeling, I'm first going to show you how to do it for a flat plate, and then we'll look at the LFS. So we're going to model a flat plate under pure moment load, and then we're going to model an LFS plate under pure moment load. However, I'm not going to do the explicit modeling in ABAQUS. I'm going to use a script that we have created in order to do this process automatically. So this is the Python script, and in order to learn how to program and how to come up with your own Python script when you're doing ABAQUS modeling, you can check back in previous videos. It's basically a command that you use that you have to activate, and then ABAQUS will basically record everything. It's called, the recording. You basically have to record a macro inside ABAQUS, and ABAQUS, as it's recording the macro as you're doing the explicit modeling, then it's automatically generating the Python script that's needed, and then you can transport that Python script and into a much more explicit file that you can start to edit to automate your modeling process. There's a tutorial video that Dean Adab had made, and you can check back in that video to look at the basics on how to do it. So this is the Python script, and we're just going to change the parameters here at the top. So we have the frequency, we have the amplitude, the depth, the thickness of the web, the thickness of the flange, and the thickness, the width of the flange, and the length of our plate. So for a flat plate, there is no frequency, there is no amplitude. For a flat plate, the frequency is basically 0. The amplitude is also 0. So the model that we're going to do is this model here that has a depth of 1 meter. The thickness of the web is 10 millimeters. The thickness of the flange is 12 millimeters. And the width of the flange is 300 millimeters or 30 centimeters. And then the full length of our beam is 8 meters. This script is written in meter. And then also the loading and the boundary conditions are already applied in the script for a simply supported beam. And so all you have to do is primarily just change the parameters at the top. For a flat plate, your frequency and amplitude will be 0. For an LFS, these two numbers will change based on the geometry that you're defining. So another thing is the loading, and we're applying a pure moment load, and I will show you how it looks like in ABAQUS, but we're applying basically 1,000 Newton meters or 1 kilonewton of unit load. So let's go to ABAQUS. Here's ABAQUS. Make sure you set your work directory already by clicking File, setting your work directory, by clicking and this icon here and selecting the folder where you want your output files to be located in. In my case, I've selected this external D drive LTB CRUE research, and you can just click OK. And then that will load your set directory for you. So now, I showed you the script, and to run a Python script in ABAQUS, it's very simple. Once you have your script saved and completed, you click on under the file to the top left, and then you scroll down all the way to where it says run script. You will click where it says run script, and then you go to the folder where you have your Python script located. And this is my folder, and then I will click on this. In my case, it's this file here called flat, frequency 0, tutorial. I'll click on that, and then I'll click OK. So what that does, ABAQUS will run the Python script for you. It will create the model. It will assign the loading, the boundary conditions, and then run the analysis for you. So, but to get to this point, you have to first learn the explicit modeling, understand the boundary condition, the loading conditions, before you can be able to automate all of your analyses. So now it looks like our analysis is completed. When we click on the part, we see that we have a flange and we have a web, and you can double click on it. You see we have a flat flange, and if we double click on it, we have a flat web. And then we've also already assigned our material properties in this case. And I can go to my loading conditions, and you see my boundary condition for simply supported beam. And then I can click the load manager and then click the edit, and you can see the load, how it's applied in the end. Basically, you have a couple moment in the end apply on the flanges. So let's look at the result. Then we can click on our module manager and then go to the job, and we see our analysis has completed, and we'll just select it and click results. And then boom, we have the results. And we see that our beam has failed in lateral torsional buckling, as you can see here, as we call it LTB failure. And this is an LTB failure. This is what we wanted to achieve. And since this is an eigenvalue analysis, we're trying to understand what is the critical moment buckling load. And in our case, it's this force here. It is 923 kilonewton. So we applied a unit load of 1 kilonewton, and the buckling load for that is 923 kilonewton for this specific beam as a flat plate. So now I'm going to repeat the same process, but we're going to do that for an LFS plate. So what we can do here, I am just going to close this, go back to my parts, and I'm going to make sure that I close the result file. And then we're going to open up a new model, start something new from scratch. I'm going to select no, I do not want to save the results. And so what we're going to do, we are going to create the new LFS model. So now let's look at the LFS script. This is the LFS script. For the LFS script, I am applying a frequency of 2.5, and the amplitude for my web, for my LFS web, is 2.5 centimeters. And these units here that you see, they are all in metric. So you have to enter them in meters or in newtons so that you can track your units as ABAQUS is running analysis for you. We're going to keep the depth the same, the thickness of the flange and the web and the width all the same. The only thing that I've changed in this script is the frequency and the amplitude in order for me to create an LFS geometry. And the loading is going to remain the same. So I'm going to save this file. Then I can go to ABAQUS and then run the script of the LFS file now, not the flat, but the LFS. So run script, and then I'm going to select my LFS tutorial file, which is this one, and then click OK. And then we wait as it's processing, generating the model, and then running the analysis. So once everything is completed, once everything looks good, then we can look at our part. We see that we have a flange. We do have a flat flange that has also the LFS partition at the center. And then we can look at the web, and we see we have now an LFS web. And we can go to the load, and we see we have our assembly with the LFS web, with the boundary and the loading conditions applies to them. So now we can go to, you can also look at the mesh to see the fineness of your mesh. And then we can now go to the job to look at our result. So our analysis has completed. We can select the analysis and click results. And then boom, now we have analysis has completed. And when we click on this, the form sheet, and then now we also have the LFS failure. Now for the LFS, the lateral torsional buckling load, the elastic lateral torsional buckling load, because all of the analyses are for the eigenvalue, so they're all only elastic analysis. We also achieve an LTB failure with the LFS, and the LTB, the M critical, or the elastic buckling, critical buckling load for this LFS geometry is 926.9 or 927 kilonewton. So we saw that for the flat, it was almost 923. For the LFS, it's 927. So we gain a 4 kilonewton by changing the geometry. So this is how you model an LFS plate, not as an explicit, but using the Python script. So I will add the Python script into the tutorial file so you can have that and you can begin to change the geometry to fit the studies that applies to your questions of research. So that's it for this tutorial video today, and I will catch you in the next tutorial training video.